In a previous video, I showed the Micro ROS demo on Pico, building a ROS2 ecosystem and connecting our Pico to it. The Pico didn't do very much, just published a counting message. When working with ROS2, it's recommended to use specific message types. So if we want to publish the temperature of our Pico, we should use a temperature message type and not just use any message type that happens to include a float. Using specific message types helps in making the robot type safe, understanding the context of what is happening and documenting our system. In this video, I'm going to show one approach to creating a custom message and publishing custom messages from our Pico. In this video, I'm going to write a new custom message for our Pico to use with the Micro ROS. That message is going to control a servo. The message will include the number of the identity of the servo and an angle for the servo in radians. We can use the message type for two things in the example. The Pico can continuously publish the current angle for each of the servos it is controlling. We can instruct the Pico to move the servos by sending a target angle message. So these will become two topics, servo's current and servo target. I've put all of the code for today's example on GitHub. A link to the repo is in the description. Before we get into it, let me introduce the sponsor for the video, PCBWay. PCBWay are a friendly manufacturer of PCBs to designs by people like you and me. PCBWay also offers services in 3D printing, CNC, sheet metal fabrication and injection molding. PCBWay have been supporting makers for 9 years and have some anniversary vouchers available right now, so go get yourself a bargain. ROS2 has three primitive communication methods: messages, which are one-way publications on a topic; services, which is a request to a particular node and gives a response; actions, which is a long-running request, which prior to getting the final response gives updates on progress. In this video, I'm going to focus on messages, but this can be applied more generally. All of these interfaces are specified using the interface definition language and ROS2's utility to compile this. In this example, I'm going to build a servo message. It will contain just 2 bits of information, the servo identity and the angle in radians. I'm going to use the same message in 2 contexts. I can use this in a request message to tell the servo to move to a specific angle. I can also use the message notification of what the current angle is. So our servo's message needs to be compiled into our system. We need the message definition on the Pico for our servo control application. We also, though, need this on the Raspberry Pi so I can command the servo and read its status. That way both our Pico and Raspberry Pi can communicate using the new servo message. The Pi asks the Pico to move the servo. The Pico tells the Pi what the current servo angle is. This means we need to cross-compile the definition of our servo to both platforms. Unfortunately, the ROS2 Colcon build generates only a single binding structure. This is held in the build and install folders within the workspace, so we use those to be the binding for a Raspberry Pi. We'll use a separate firmware folder and subfolders for the Pico binding. To build the binding, we also need all of the supporting code for the Micro ROS library, so actually end up rebuilding the Micro ROS library and placing our custom message within that library. This works and seems to be the recommended approach, but it's not ideal. It takes me the best part of an hour to rebuild the library. That truly slows down my iterative development. This has made me think a few times of standardizing on just 3 messages to encode everything as JSON. This would remove the type-safe nature of ROS and avoid some of the design principles, so this isn't the idea. Our project structure needs 2 parts to it. We need our normal Pico project source and makefiles, represented here by the token src folder. It also needs us to build the new custom message in ROS. We therefore also need a Micro ROS workspace. I'm going to zip through some of the pieces of setting up the workspace and standard ROS build approach. I'll focus into the Micro ROS approaches instead. I'll put some links to the guides on the standard ROS build into the description and also on my blog site .johnea.co.uk. In my notes is the long list of commands to get this built. So let me break it down into 3 steps and link you to some articles that explain these in more detail. We need to set up a ROS2 workspace and put in that the Micro ROS setup package. Then we can create our custom new package for our servo message. Finally, we can set up and do the cross compilation. Let's start by setting up the ROS workspace and the Micro ROS setup project. The first step is to create our workspace for the Micro ROS. We need to be using a specific version of ROS, and I'm going to use Humble, then a folder in my project called Micro ROS Workspace. I'm going to add a submodule to this workspace of Micro ROS Setup. This contains the build system for the Micro ROS library. Like any new ROS package, we now need to resolve the dependencies and initialize the build, then source the environment. This is important because we're going to need to run some scripts from within this Micro ROS Setup package to be able to cross-compile. Now let's turn our attention to our new custom package and servo message definition. There are excellent tutorials on this from ROS2 site. Largely this is covered by Create Your First ROS2 package and Create the Custom Message and Service File tutorials. I'll put links to these in the description. So we can create a new package called ROS2 Servo. In here, I'm going to write the message definition. I'll need to update the cmakelist.txt file and the package file to reflect that we're using IDL and the new message. Then we can build the package. I'm building this package for the Raspberry Pi side rather than the Pico at the moment. I still need the definitions built for the Raspberry Pi side to be able to interact with this message. I'm going to also cheat a little bit and place a script to help with the cross-compilation setup in this package. Without building the package, I would not be able to run that script within the ROS2 environment. We have already talked about the message definition. This is going to live in the servo.message file, right now in the structure on the right here. When you generate a package, you get a default cmakelist.txt file. We need to do some updates to this to prepare for the cross-compilation. Register the new message and include the IDL generation in the build. Firstly, we're not going to use standard libraries on our Pico, and I'm going to turn shared libraries build off. We're using the IDL system to generate our interface, so I need to put the definition in for this. I also need to inform the generator of what our messages are, so our new servo.message file is listed in here. Finally, I've included a script to create the firmware workspace setup. The script may not be perfect, but it should be generic enough for other message packages. We also have a default package.xml file. Again, we need to do some updates to this. Of course, that includes updating the standard bump around author, description and licenses. It's also key though that we add in these lines for the dependencies on the IDL generation process. Remember, the detail is all on GitHub, so you can look at everything I'm setting up so far. We're now finally able to compile and generate the new library, including our custom message. Most of the process is documented in the Create Custom Static Libraries tutorial over on the Micro ROS website. We use the Micro ROS setup package to create a firmware workspace, telling it that we want to generate a library. For some other microcontrollers, the full build process can be done under ROS, and so not everything is targeted at library process. We're going to need to tell the build system about the toolchain for the Pico. We do that by providing 2 files, the mytoolchain.cmake and the mycolcon.meta. I'll talk about these in a second. We can now run the ROS2 servo workspace create function 2. This will copy the source code for our message into the firmware workspace. Finally, we can kick off the build using the MicroROS setup package, telling it where to find the toolchain and Toolchain configuration for cross-compilation. What we've done is created this structure. The MicroROS setup workspace has been created under the firmware folder. The key one here is the MCU workspace, which contains the code to build into the library. Under the ROS2 Servo create workspace script, I've copied the code for ROS2 Servo to be under the MCU workspace. We also have the Toolchain configuration file. Let's chat about them now. The Toolchain CMake file defines the build for the cross compilation. So this is linking into the Pico toolchain and the Pico SDK. It looks close to the top half of the standard CMake file for any Pico project. The Toolchain meta file contains a set of build flags for the MicroROS, which I've used is the standard set from the tutorial on the MicroROS website. I'm currently building this on a Raspberry Pi, and it's not a quick build. So after the best part of an hour, I'll have the libraries and include files under the firmware build folder. We can now use this to build some firmware for our Pico. Cool! So firmware time. Our firmware is going to do two things. It's going to publish the current servo position by the servo current topic, then listen to new target angles to set the servo to via the servo target topic. The publication of the servo current is going to be done using a timer. This is very similar to the MicroROS Pico demo I showed in the previous video. The servo target topic uses a subscribe service and provides a callback function. This callback function will then interface to the servo. I'm going to put all the code to manage a servo into a servo class, so we can get the angle in radians to be able to publish that. We can also move the servo using the goRad method to go to the angle represented by radians. To manage the servo, I'm using PWM and controlling the pulse width. I've got a short video which shows how PWM can control servos. Go check that out, link in the description. All the code for this is on GitHub. I'm just going to point to a couple of snippets. We're going to use a couple of libraries, the Pico SDK hardware PWM library to manage the servo, and also the MicroROS library. I've written a MicroROS CMake include file to link to the library and include folders we built in the last section. The publish part of our code is very similar to the MicroROS demo. We set up a publisher and use a timer to trigger that publish step. In this example, each time the timer fires, I'm going to publish one message for each servo I am controlling. I just need to populate the message with the servo number and the angle in radians. Subscribe is not that different. We need to initialize a subscriber for the servo target topic. Then we add that into the executor, giving the callback function to call when new data arrives. The callback function itself casts the message into the right structure and then asks the servo to move to the instructed angle. So we have everything we need to build this firmware and flash the Pico. To get our Pico and ROS2 environment on my Raspberry Pi to talk, I need to run up the MicroROS agent. Then I can use the ROS2 environment of my Raspberry Pi to see the current servo angle being published. I can also use the pub utility to publish a new angle for the servo to move to. So here I have a servo moving between 0, 90 and 180 degrees and back again. I'm just using the pub utility to push out the new angles. Performance isn't that great, but I think this is due to the work being done by the pub utility to validate and connect each time. Of course, if I can run one servo, then I can run several. The Pico will support 16 PWM channels and therefore 16 servos. I'm just going to run two with a little pan and tilt model with a laser diode to make it look a bit cool. Though I've only shown a custom message in this video, we could use the same approach to reduce the two other communication primitives of services and actions. Needing to rebuild the whole firmware library for for Micro ROS for each new message type I don't think is ideal. What do you think? Is there a better way to do this? Thank you very much for watching. Please do like the video as it helps others find out. Please subscribe and hit that notification button for more videos from me. Goodbye for now.